Okay, and so yeah, well, welcome everybody. I'm really excited to be part of this amazing webinar slash workshop slash course, and to talk to you about something near and dear to my heart, which is multisensory XR experiences. So jump right in. I want to talk a little bit about the role the HIT Lab plays in ARIVE. Again, Holger's asked me to talk on multisensory XR because that's one of the things that we really specialize in. This ARIVE network is really great because it brings together a lot of capacity. And we mainly focus on multisensory XR applied games, and then long-term immersion, cyber sickness mitigation, reducing fatigue, really kind of allowing people, working on the problems on the edges that allow people to stay in VR for a long period of time. So integrating VR and XR into your workplace, for example, is something we're working on very actively. And as with everything around ARIVE, it's all tied together through AR, VR, XR, STAR-R. So that's what makes it really fun. So I want to actually, it's interesting the way Holger introduced my work. There is a bit of confusion around multisensory versus multimodal. And I've been preaching this for a while. When I first started working on multisensory research, some papers and a lot of researchers talk about multimodal and multisensory. And these terms are used a lot, sometimes to mean the same thing. What I'm trying to really push is that we split these into two very distinct and identifiable terms. So I use the term multimodal exclusively for things that deal with input to the system from the user. So I speak and I point. So this is multimodal input. So I use multiple modes to give input. And multisensory is the feedback or the output to the user. So I'm giving stimulation to the eyes, the ears, the hands, and all of that is multisensory, and that my senses, I'm using multiples of my senses to work on it. So thank you, Holger. You walked right into it for me and you introduced this as a multimodal talk, but it's really multisensory. But anyway, there's a lot of discussion about terms. I just think that multisensory makes it more clear. So anyway, so what I'm going to talk about today is, or what I want you to think about is current systems do graphics and sound really well. So we definitely have, let's see more of that. We definitely have systems such as game engines and the graphics rendering hardware that does a really great job with graphics, and sound is also pretty good. And these are pretty well integrated together, and they're pretty well understood. So we understand the visual system, the way the eyes work. We understand the problems with the eyes. Also, we understand how sound works really well, and we understand the cues that can be used to make sound very rich, realistic, or whatever we're getting at. The hardware is really mature, so we have great rendering hardware, we have really good sound cards and these things. And these senses, by their very nature, are very non-intrusive. So I don't need to actually touch you in order to feed the eyes or the ears. I can do that without really touching the body. So these make them actually really easy to address. Also, many would claim that they're the primary senses. So vision and auditor and audio are kind of our primary senses. So it makes sense to focus on these. So that's great. So what I'm really interested in this case is what's necessary to get us to the next level. And that's kind of beyond visuals and sound. So a little bit of motivation for me. And again, I got a lot of my early motivation from books. So here's a smattering of books that you should read if they're not on your bookshelf. You should check them out if they're not on your Kindle or whatever. These are just really nice, rich descriptions of VR that has motivated a lot of us. If you'd rather consume things a little more quickly, you can watch films like The Matrix or Existence, which unfortunately came out the same year as The Matrix and is it's more about video games than life or VR, but is also an interesting film. Some would say a bad film, but anyway, an interesting film. And then again, reaching back all the way to 1972, where we had robots instead of avatars, but these were worlds that people would go for a holiday, and there's a West world and a Roman world and so on. And so these are also kind of alternate realities. And then finally, kind of more recently is Ready Player One, which probably many of you have seen, but also has some really interesting drivers for the technology. The book is also really good. So when we talk about virtual reality, typically in my dissertation, gave this definition, which is fooling the senses into believing they're experiencing something they're not actually experiencing. So if we think about this, it's all of the senses. So it's not just as in Milgram's paper and a lot of early work in Ranazuma's work, it really they all seem to focus on visual aspects. And I've always thought that we really need to think about things in a more multisensory way. So really fooling all the senses. So you really want to do as much as we can to promote realism or whatever it is we're trying to get people to believe. And I have updated this in the meantime. It actually still holds water pretty well, but I think we actually need to fool the brain and not just the senses. The senses are really just a vehicle to get to the brain. So we really want the brain to believe what we're doing. And we can do that actually not by pushing harder and harder and making things more real, but sometimes pulling back and allowing the brain to fill in the gaps. So what I call experiential fidelity. So the idea is that you bring with you into any situation baggage, previous understanding of the world, and that it's actually better to just give you a sense of something and then allow your brain to fill in the richness of your understanding of what that thing is. So I always use the example of Alien, the first Alien movie, which is really, really scary, but you never actually get to see the alien. You hear the alien and you see the goo that they leave behind and you hear people screaming, but you never really get to see it. And you're really scared. And I think the reason for that is the filmmaker really made it so that you have to use your imagination to fill in the gaps. And I think that's actually really powerful. So if we think about the components of VR, we have users, content, graphical audio, haptic rendering of some kind, so displays, tracking of objects and people, physics, interaction techniques, which is near and dear to a lot of people's hearts here. And sometimes there's networking and autonomous agents of some kind. And I would claim that the user is really at the center of all this. And the reason we're doing all of this is for the user's benefit, not so we can render faster, not so we can make collisions better. It's really so that the user has the best experience they can. So I've used this slide before, but if we think about reality, the famous philosopher Qui-Gon Jinn tells us that your focus determines your reality. So we really need to have people focus on things and to really surround them, and so that what they're experiencing is engaging. And then that will determine how much they believe it. So we can really translate this into that reality really doesn't exist. And there's a lot of online conversations about the matrix and so on. So reality is really just an illusion. So let's actually fake it. And faking it doesn't mean cheating. It means using the essence of what you're trying to get across. And I would say we need to do that really in a multisensory or holistic approach. So we can think about this, and again, many VR researchers, you've probably seen this slide maybe 3 or 4 times in this series. But I actually went and dug out the patent for the original patent by Mort Heilig. And this Sensorama also had this idea of trying to use multiple sensory things. So it does 3D, has wide vision, whatever that meant at the time, some motion, so the graphics actually moved. It was in color, it was groundbreaking, stereo sound, there were aromas that it emitted, wind, and the seat vibrated, so this was a motorcycle experience. But already we're seeing the introduction of this kind of sensory stimulation in concert, which is great. So what I did when I really started to think about this is to try and think of where can we mix reality. So if we think about that mixed reality environments take some aspects of the real world, take some aspects of the virtual world, and somehow mix them. One question is, where could we do this mixing? And I found this to be, this was actually not an off-cited paper, but it's really one of my favorite papers that I've written, because it really, I think, sets up a nice framework for how to think about this notion of mixing reality. And this is work I did with Haruo Noma, then at ATR and now at Ritsumeikan in Japan. And we did this work when I was there as a summer researcher one summer, and really kind of explored this a bit. So if we think about the pathway from stimuli to the brain, we have this real world pathway where there's some signal, let's say there's light, some imagery that's traveling. We see it through the environment, so that the signals pass through the environment. They reach our sensory system, so it could be our ears or our eyes. And then there's some translation that's done that makes that into signals on the nerve. Then the nerve goes to the brain. So again, this is a relatively simplified diagram and doesn't talk about the intricacies of different sensory subsystems, for example. And but anyway, for us, this was the right level of detail to think about this. And we could think about mixing, for example, at point number 1, that says if we take some computer-generated stimulus and we mix it in the environment somehow, then the sensory system will pick it up and pass it on to the nerves and then go to the brain. So we can think about this as kind of maybe projection-based systems where we have the real world and we project some virtual content on it. It's mixed in the world and then the sensory system processes it. We could also try to mix at the sensory system. So within the sensory system. We could also try and tap directly into the nerves. So maybe this is direct cortical stimulation or something like this, like you'd have maybe in the Matrix. We could go directly into the brain and stimulate there. So you could think about this as let's think about which technologies you might slot into each one of these 4 positions, and then think about what that means. Like, what are the good and bad aspects of doing that? Of course, tapping into the brain maybe has several bad aspects, but we'll leave that out for a second. So the direct path of real stimuli is what's shown here at the top. If I think about captured stimuli, so a lot of what we do is we use cameras or we use microphones to capture stimuli and somehow process it. So you have a real world image, it goes through the environment. I have a capture device like a camera. I'm going to capture that. I'm going to post-process it in some way, and then I'm going to produce a captured signal that I can then introduce at one of these 4 points, 1, 2, 3, or 4, right? So I somehow have captured things. If I have this notion of using cameras or microphones, it could be purely computer generated, in which case I have not a captured signal, but a computer generated signal. But you get the idea. There are pluses and minuses to capturing versus computer generating. So, okay, so I'm actually gonna use this framework through a lot of the talk and tap into this notion of where we do the mixing. But I'm gonna talk about it in a holistic way. So I'm really gonna address all of these senses and then talk how they interplay with each other. So we see here smell, touch, and taste our world. So we have the visual sense, oral sense, olfactory, which is smell, haptic, which is touch, and gustatory, which is a word I learned when I first started working on this, is the sense of taste. And again, I would claim that visuals and audio were doing really, really well. Smell is really hard because of the sensing, the way the nose does some sensing. Touch is usually very cumbersome or very simplistic, and it's usually, when it's effective, it's usually application specific. And taste, we know about the 4, or if you're Japanese, 5 base tastes, but that's really it. We are learning a lot more about these things. But these last 3 are intrusive to actually give some sort of stimulus. You have to touch the body in some way. So if you want somebody to smell something, it's an invasive thing to have it go into their body, and it changes the person somehow. So anyway, so if we think about where we're doing this mixing, we can, as I mentioned, this gray is a person in the physical world. And there's a PC, so they're looking into the real world, and I'm projecting computer-generated content in the real world, and then comes in through the eyes, and we have this process. So this is mixing in the environment far away from the person, I would say. You could also think about things like optical see-through. So here, I'm mixing in the environment, and that the person, now the PC is generating some content, it's being fed to some glasses, and I'm looking through the glasses at the real world, but I still see the computer-generated content. It's still mixed outside of my eyes, but it's closer to my eyes. So you could even think about this proximity, which can be important for certain technologies. So these are things like the HoloLens 2 and the Magic Leap. All right. We can also think about video see-through. So here now we have a mediated, computer-mediated capture of the real world. So I have an opaque or non-transparent head-mounted display, and I have a camera mounted on the front of the display. It captures the real world, which is sent to the PC, which does some processing, and then that's sent along with the computer-generated imagery. I combine the real-world imagery in the computer. So the mixing is happening in the computer and then sent to my eyes somehow. So here, so this represents AR. And there's headsets available for this. So I'm not going to talk about these much, but there's a wide availability of different headsets that have cameras in them, and they capture them and allow you to mix them. So Microsoft Mixed Reality Platforms is an example of this. And then we have the totally occlusive headsets, well, some of them. So these are, again, looking at the cost changes over time. So these are a smattering of the early headsets or early commercial headsets. The one on the left, the CyberMax, is the first one that I used and played Doom on that in 1995 for like 6 hours straight. And that was when I was definitely hooked and I knew what I was going to do with the rest of my life. And through units like the Glastron, which was in research labs, very, very heavily used, and provided, again, some see-through as some of these other devices do as well. The price stayed about the same, except Sony seems to always cost more. But the resolution got better and better. So this is, again, these aren't the latest technologies, but these are the next wave came with these. And so we have actually really, 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 really good support. And they're only going to get better and cheaper and faster and everything else for visual displays. And we still have these low-cost ones, though the Oculus Go is now no longer made, unfortunately, because I still think that was a pretty sweet spot for a low-end device. But we have there's lots more devices that are coming on the market or on the market now. So this will just get better and cheaper. The Quest, for example, is not listed here, and so on. For visuals, we also have things like projection displays. So these are classic versions of the cave, where you stand inside and the walls are projected, either front or rear projected, and you feel like you're kind of holodecky or you're inside a space. They're projected, you get images that look kind of like this, and they allow you to, again, be immersed in the content, even though the displays are far away from your eyes. You're still immersed, surrounded by the content. So again, I'm not going to talk that much about visuals and sound, but they lay a really good groundwork for what I'm going to talk about in terms of multisensory stuff. So if we look at the same model, but now we've replaced the sensory subsystem with an ear system. So we have the real world sounds. They pass through the world and the environment. They're changed somehow. And then they reach the ear system, which then gets translated into nerves in the brain. Again, this is oversimplified, but we have the outer ear. So with Pinay, we have the middle ear, we have the inner ear. And so we can think about mixing in the environment again. So somehow mixing computer-generated audio with real-world ambient sound. We could think about mixing somewhere in the ear system. And again, we can mix in the nerves in the brain, but I'm not going to talk too much about that. But again, for completeness, we could do that if we wanted to. And we can actually think about mixing at the outer ear or the inner ear in particular is what is approaches that I've been looking at. So typical AR and VR systems use either speakers. So if you think about a cave or where you're standing in a large projection scene, you might have speakers that are producing audio of a person speaking over here, but the audio is being mixed in such a way that they sound like they're coming from over there. But I can still hear the real world or other people that are in the room. Or they use something like headphones, which would be mixed at 2A. So I have headphones on that are somehow where I'm feeding computer-generated audio to the ear that way. You could also, though, perform the mixing at the cochlea. So we've done a lot of work exploring the use of bone conduction devices. So a bone conduction device sits out, doesn't cover your ears, but still stimulates your ear canal and or the cochlea. I'll talk about that a little bit. So graphically, if we think about this, acoustic, so we coined this term again in 2007, acoustic hear-through AR. So just like you have see-through, so video see-through, and optical see-through in the visual domain, similar to optical see-through, we have acoustic hear-through augmented reality. So this would be something like speakers. So your ears are unoccluded, and you have either 2 or 4 or 6 or some number of speakers, and you can do things like, I have real people in the real world, and I can see them and I can hear them, because my ears are not covered, but I could also put a virtual person in a certain place, and I could, using AR, I could use the headset to project the visuals so I could see them, and then I could use the speakers and mix the sound coming from that person in such a way from the PC to make it sound like the person's voice is coming from where I see them. So I have, again, real people and a virtual person, and this virtual person is both there visually and auditorily. So again, there's a lot of parallel between the visual and audio domain. Mic through AR doesn't use speakers, but does mixing in the computer. So what we do here is the PC is producing sounds that I hear through headphones, but then I put some small microphones outside of the headphones. So what we've done here is we've literally glued microphones onto earbuds. So you take these earbuds and you put them in, and the microphones capture the sound around them and send that to the PC. The PC takes that, mix it with the CG audio, and feeds that back to the headset. So very similar to a camera capturing the world in video see-through, these capture the audio space and feed it back using this, what we call mic through AR. And this allows me to do something very similar. I have 2 real people over here and a virtual person over here. And now I can hear these people talking through the microphones, and the sound that reaches the microphones will be similar to what I would normally hear because there's 2 microphones and I only have 2 ears. But the virtual sound is then computer generated and mixed, and now I don't have to have speakers in the environment. And another way to do this, so this is mic through AR, this is hear through AR. So hear through AR uses bone conduction, and it's mixing at the sensory subsystem. So the PC generates an audio signal that gets sent to my younger head. This is my younger head. And I'm wearing this bone conduction device here, and it doesn't cover my ear, but it sits next to my ear on my cheekbones. There are 2 bones that stick out here. Some of them sit on the mastoid, which is just behind the ear, a nice prominent bone there. People with cochlear implants typically have an anchor drilled here, and then they put an actuator on it to stimulate the cochlea. So the idea here is that, again, since my ear is unoccluded, I hear the real people around me, and I hear the virtual person through this bone conduction device that's generated, where the audio signal is generated by the computer, and then the mixing happens in my cochlea because these bone conduction devices don't make sound, they make vibration, but the vibration shakes my cochlea and allows me to hear things. So it's an interesting device. And again, we've done work on this. So because it's hard to know what this sounds like, I'm going to show 3 examples of sound. So when we hear our own voice, we hear air conducted sound, so sound that comes out of my mouth and goes into my ear. And we hear bone conducted sound, which is my voice box is shaking, which shakes the bones. And so I hear these low frequency, typically low frequency sounds that reach my cochlea. And those combine with the air conducted sounds, and they're combined. So I'm going to play audio, and hopefully this will come through because I set things correctly. Yeah, should come through. So let me try this one. So this is sound that you hear through the air.
Hey, Ma! Get off the dang roof!
Is that hearable? Hope so. I'll play it one more time.
Hey, Ma! Get off the dang roof!
So if you've ever heard your voice recorded, you know it always sounds higher, and that's because you're only hearing the air conducted sounds, and you don't hear the bone conducted sounds. So here's just what you hear through your head.
Hey, Ma! Get off the dang roof!
I'll play that again. I don't know how well this is coming through.
Hey, Ma! Get off the dang roof!
And we combine these together, we get something like this.
Hey, Ma! Get off the dang roof!
Just to compare one more time with only the air conducted.
Hey, Ma! Get off the dang roof!
Okay, so that's kind of what it sounds like. Again, it's really hard to demo this stuff, but that's the best that I found. And thank you, Clovis, for helping us. Okay, so as I said, I'm not going to talk that much about audio, though I guess I have talked that much about audio, but we'll just let that go. I'm going to talk now about smell, touch, and taste. The olfactory sense is a very, very interesting topic to cover. And as I like to say, the Japanese have done a lot of work in these senses because the Japanese in general are just crazy and they just build really cool stuff. So I've had the privilege of working with really interesting researchers in Japan around some of these problems. So in general, the way the research around the olfactory sense is configured is two main problems. And again, these can be divided different ways, but in general, generating the scent and delivering the scent. So if you think about creating a strawberry smell, you need to somehow combine chemicals together that are going to produce a strawberry smell. That's a really hard problem, though there are people that work on it. There are scent designers and things that work on these problems, but it's really hard to do kind of immediately, like combining RG and B to get millions of colors. So scent generation, knowing what to mix together to get strawberry versus chili pepper, those are two very different things. The other problem is delivering the scent. So once you've produced it, how do you get it to the nose? And I'm going to talk primarily exclusively about the second of these problems because even that is an interesting problem to look at. So some of the things have been done, and again, I'm using the same approach as before, this mixing. Where do we mix? So if we think about mixing in the computer, if we say that what I want to be able to do is to deliver a smell to a participant. Here we have somebody wearing a mask, and we have 3 vials, and each one has a different smell in it. And this device can switch between these 3 different smells and fresh air. So if the computer wants you to smell strawberry, it opens up this chamber and pumps strawberry into your, so you can smell it, and then it clears it out with some fresh air. So you can switch here, the computer can switch between these different smells. Another really interesting approach is using what's called an air cannon. So this mixes in the environment. So what happens here is you have this device that will shoot a scented smoke ring at your nose. And there's a chamber here, and you can fill the chamber with whatever smell you want. So if you want strawberry, you fill the chamber with strawberry. And then the computer, it's on a pan-tilt platform, and the computer will follow your nose. So basically, instead of an eye tracker, there's a nose tracker. It tracks where your nose is, and when it's time, it will launch a scented smoke ring at your nose. So when they want you to smell, in this case, lemon, they'll fire a lemon-scented smoke ring at you, and it'll hit your nose, and you'll smell. So when you have your virtual reality headset on, you'll be in, let's say, a lemon grove, and you'll actually smell the lemon. This is a very interesting approach. This is a later version of the same, what I call the Darth Vader version by the same group, by Yanagita's group. And this has, again, a number of different scents that it can bring in. It has a bellows, so the bellows pull back, and a valve is opened before it pulls back, and that scent is drawn in. The valve closes, and then at the very front, there's another another aperture, and this thing's on a pan-tilt platform, and when it's time, it fires the scent at you. Another approach is using a boom. So this is a boom mic with a tube on the end, and these are a number of different odors that are inside this carousel, and this device can choose which odor to then pump through this tube that you then smell. And you can also smell the real world. So if you notice, this doesn't cover the nose. This one doesn't cover the nose. And so you can mix these smells in the real world if there's something interesting for the person to smell. But you notice that in all of these cases, they're really only focusing on smell. So they're not really looking at other things. So I have a short video that shows this. And so again, this is pretty old from when I was working in Japan again for in a different summer. So this is a simple fiberglass box, and it has a rubber sheet on the back with two actuators, two solenoids, and they basically pump the smell out that way. This one does nose tracking, so there's a little camera here, and it's looking at the nose, and as she moves around, this thing will track her position. And now that what they've done is they've put a speaker here, and the speaker they send a signal to that vibrates, and that pushes air out through the aperture. I don't know how they captured this, but they captured it. So here's the camera, and it's tracking her nose, and this is a pan-tilt platform. And so when it's time, then the computer will shoot, fill this chamber, fill with the sound, with the smell, and then fire it at the nose. Crazy, crazy stuff. So I'm going to leave smell behind and move on to touch, because touch is actually also one of my favorite things. So the interesting thing about touch, I think, is that it's really kind of the catch-all sense for everything else. So we know what vision is, we know what sound is, and we know what taste is, and we know what smell is. Everything else is put under haptics or touch. So any sort of force or pressure, when something is slippery, if there's vibration, when I feel wind, if there's temperature changes, pain, proprioception, which is knowing where your hands are or your feet are without looking at them, even the sense of balance, all of this is kind of put under this system, by us researchers who try and simplify things, under haptics. So it's very, very hard to study, because what are you talking about? Or what part of the haptics thing? Most people think about collisions or touching things, but it actually means all of these things. So if we think about just the tactile and kinesthetic displays, so tactile typically has to do with the surface properties of the skin. So the skin layers are made up of 5 mechanoreceptors, and mechanoreceptors have different properties, so they sense things in different ways. Some sense pressure better than vibration, and so on. Some sense shear motion versus pressure, and so on. So these have been developed over millennia. Whereas the kinesthetic sense is more the muscles and the tendons, and we have sensors in our joints, so I don't need to look at my elbow, but I can see, I know where my hand is because I have sensors in my joints that let me know where it is. So even without looking, I can touch my hand because I have these sensors in there. And the image on the right is the homunculus man, and this is a very common thing that's used in haptics research to describe the sensitivity of the body. So the size of the different parts of this man's body are drawn in relation to the larger they are, the higher the density of the sensory mechanoreceptors are. So the hands are huge. So we've developed over through evolution to be very, very sensitive hands because we need to survive. Same with around the lips. But you notice that the torso is really small. So the sensing or the resolution of how well we can sense on the torso is actually very low resolution, whereas the hands are really high. So the density of receptors in the fingertips, for example, is extremely high, as is the tongue and the lips and everything else. So we need to know this because when we make displays for haptics, we need to figure out how much resolution do we need. For example, it might be like, oh, I'm making a vest. I need to get these actuators really, really close to each other. Well, it turns out that by some research, the 2-point limit, so the best I can do of determining the distance between 2 points on the torso is, let's say, 3 or 4 centimeters. So there's a discrimination test that you can do where you basically poke somebody with either 1 or 2 pins, and you ask them, how many did you feel? And by doing this on different parts of the body, they get these thresholds. And so you can figure out that on the nose, for example, there's a 7 millimeter density, whereas on the foot, it's 20 millimeters. On the belly, it's 30 millimeters. The forearm is 35 millimeters. So if you're gonna build some sort of vest or suit, you actually don't need to have really, really tightly spaced actuators, you actually have a lot more freedom, right? So this is extremely important if we want to do anything in terms of designing displays of some kind. So we can think about the properties of these. Another really interesting point is the haptic sense is really the only one that's bidirectional. So it senses the environment. When I pick up something, I'm sensing its weight, its temperature, and everything else, but it also acts on the environment. So vision, I'm passive. I just receive visual cues. I receive audio cues. Taste, we could argue about. But it's clear that when I touch something, I am acting on it, but I'm also sensing at the same time. And this tight coupling also makes it really, really hard for us to do competent research in this, because there's this very, very tight coupling, and we know when things are mismatched very, very easily. The other thing is the skin is the largest organ in the body, and as I showed before, it's not, the sensors are not uniformly distributed. So it's a really, really tough problem for us is to come up with a general haptic solution. It's just not going to happen. And it's really not, maybe we need to do something closer to the brain. But it's just extremely hard to do something that's a general solution to haptics. And again, I've done a lot of work in it. I'm really interested in haptics. But what I found is that something is better than nothing. That's kind of the short answer to working on haptics. So if we think about different things that have been tried, people have tried pin arrays to give some sort of surface properties, force feedback arms that allow you to give force feedback when you push on something, little shaking pager motors. So this is, for instance, what's used obviously in your phone, but also if you open up, as I have, a PlayStation controller, in the wings on the handles, you'll find two weights that are on DC motors. And there's a big weight over here and a small weight over here. And basically when you apply a voltage, they shake, and because the weights are off center, they spin and they shake. A very, very simple device, but it provides some haptic feedback somehow. Particle breaks, passive haptics is something that I pioneered in the 90s that really just looks at the properties of objects themselves. And the best solutions here are going to be something that's very specific. If you're building a surgical simulator, then that's a haptic device that's going to be very, very purpose-built, but it's probably not going to be useful for other things. And those have been the best types of things, as opposed to things that are more general purpose. So my PhD work was around bimanual input using these passive haptic things. So this is literally just a piece of wood. I actually think I have it. Yeah, sorry. I still have it here. So it's literally just a piece of wood, and I put a tracking device on the back. And the person, what I do is, since it's tracked, is I display at that time very rich graphical user interfaces on the surface of the paddle. I'm tracking their finger, so I can do user interaction using this paddle. And it's really nice because it's a very stable surface, so I can make very precise movements. And I show in my work how it's better than pointing in space or doing something else. So this was the origin of passive haptics. Is an object that I can put visual or auditory properties onto and allow me to interact with. And it's very, very high resolution. So my finger is getting very, very high resolution feedback stimulation just because it's a physical surface. So it sounds really dumb, but it's a really, really powerful way to do haptic feedback cheaply, but very specifically. Since then, other people have tried things like putting up, this is a project at UNC called the Being There Project. And what they did is they modeled a virtual world, and then they built a physical version of it, and then they projected onto it, or they used an HMD. And so now, if I reach out and touch the virtual wall, I actually feel the physical wall. And this was done, including in Fred Brooks' kitchen. They had versions of it and mocked up. So you could, again, just build this environment, which sounds really odd because it's really hard to change it. But anyway, depending on what you're doing, this can make a lot of sense. So one of the things we often use touch for is virtual contact. So you can think about it is that when you know you've made contact with something, what should we do? So right now, when you hit an object or something like that, usually you hear or a bump or a bing or something like that. So you can play a sound. So the way we've been thinking about this, if you think about, so usually virtual environments are doing collision detection of some kind. And so the collision detection subsystem is doing what it does. It then provides you with the collision information. The question is, what do we do? So the input to a virtual contact system is the output of this collision detection system. And the question is, do you play a sound? Do you push the user back? Do you give them a shaking vibration on the controller? And so it's actually really easy to integrate this because you're already doing collision detection. The hard part, or the expensive part, is being done. The hard part is actually figuring out how to display these cues. If somebody's gripping hard versus soft, how do you do this? So for us, we've done these are vibrotactile, what we'll call them vibrotactile in this case. And what we've done here is we've used a number of these kind of eccentric, what are called eccentric DC motors, and we've ruggedized them. Here on the right is a ruggedized version of this one. And you can see they're pretty small. And then we take this and we put them on the body in different places. So Angus Rupert pioneered this for pilots back in the day. And then we built a version, again, this is Yanagita, the guy who built the air cannon when I was doing the smell section. And he came to visit me in DC, in Washington, DC, and we visited the Naval Research Labs. And we had developed this vest the previous summer. And the vest has 16 of these pager motors at traditional points of contact. So we put them on the elbows, we put them across the shoulder blades, on the torso, on the pectoral muscles. And this is one of my my trusty undergraduate students wearing it. He's got a head-mounted display on. He's running around in a dungeon, and he's feeling the contact information when he bumps into things. And this was used for a dismounted infantry simulator where here's a head-mounted display. They have a pretend rifle. They have a flak jacket on. They have a full pack on, and they can run around and feel contact as they're running around. So if we
right now on Daily Planet, introducing touch to the virtual world. The Tactivest lets you feel everything you can see in a simulated environment.
Plus, looking good computers, where sight and sound combine to create.
So this is work that I did as a very young me at my previous place at WPI, and basically working on this. The Discovery Channel came and did a bit on this Tactivest.
To our virtual repertoire.
It's very immersive. Until you really experience it yourself, there's nothing quite like it. It really is like being in the space.
16.
What we've done is
Very immersive.
so the Tactivest is actually made up of a number of pieces. Because humans come in different shapes and sizes, what we've done is constructed the vest so that it's adjustable.
What Eric's wearing is simple yet ingenious. 16 standard pager motors are wired together, attached to neoprene. The pieces of neoprene fit together to form an adjustable vest, ensuring that all the motors remain in contact Eric's body. In traditional video games, if you run into something, you might hear a thud. But if you're wearing the Tactivest, you'll feel the impact. And if you just brush against a wall, you'll feel that differently.
What we want to be able.
Okay, so I'll stop it there. So again, this was back. When was that? That was 2004. So if you think about where we are now, nobody's really using that vest, right? So we do, but it hasn't really taken off. And if you think about it, it's really hard to build things for people because people are all different shapes and sizes. So getting these things to stay against the skin is actually really hard. So that's part of the problem with doing haptics is if it's not touching your body, you won't be able to feel it unless it's a projection thing. So some other examples of mixing. So mixing in the computer. So this on the left is an active glove. So you wear this and it can stop your movement. It's called the cyber grasp. Other types of devices like the Novin Falcon. So this is, you grab this ball and it gives you kind of 3 degrees of freedom. You can use this to explore a virtual surface of some kind. We've also done some work on wind. So right, what this is a cave. It's just showing windows right now, but it's a cave. And then there are some tracking cameras here. And in between the tracking cameras, we've added fans. And these fans will then, since this guy's head is tracked, the fans will know where he is and they will continue blowing on him as he moves around in the space. And the idea here is to provide wind feedback in windy environments, in this case, an outdoor environment. So this is how this looks. So you can see the fans up here, and they kick on when it's time for them to start blowing. And as he moves around, you can see them just kind of moving. And again, so the idea is this is some kind of haptic feedback, but you don't have to wear anything. You have to instrument the environment, but you don't have to wear anything. So another thing we try to do is the floor. So we can shake the floor. That way, just by standing or sitting on something, you can feel this vibration. So if an object explodes, you can feel that explosion, the floor shakes. If somebody walks by you, you might feel their footsteps. And so we have this Tactivest, which gives you vibrations you could wear. We combine this with the floor. And so I'll play this now. This is, again, the same setup. So we've added the fans, and we also added
Hard to see.
4 feet. You can't hear this very well, but right in the middle is the higher vibrations. Just hear the audio.
So now I think if you increase the fall off, if you increase the fall off now, it will match the size of the cube more.
I see. Yep.
I think.
So what we've done is we've placed kind of low frequency activators outside the screens, bolted to the floor. And then we can change how much each of them vibrates in order to provide, again, some amount of floor vibration. And if something explodes and you're in the cave, you see it explode, you feel the wind blowing on you, and you feel the ground shake at the same time. So here's the latest version. So this I just shot last week, where we put it all together again. So this is a new generation of the floor that we've built that you'll see. You'll see we also have a smell feedback system where we can inject scent, and I'll point to that. This right now is in, it says that you're in a pickup truck or a ute, and you're a passenger, and you're riding along, and this is all done in Unreal. This is our floor that has the low frequency actuators below it. And then we have our scent feedback system here, which we're designing. And so we can inject smell into the environment as you're going around. And then these are the fans. This is kind of the same technology, the next version of the technology that I showed in the previous slides. You can see the fans spinning. And again, the idea is to provide all of this feedback in concert. So how do we author, for example, when something should happen? How do we decide, oh, you're in orange grove, I need to make sure that the orange smell is being played. Oh, it's windy, so I need, the wind is coming from the east, so I need to make these fans blow at this speed. So by putting this all together, we feel like we can get a more realistic experience. The question is, does it make a difference? So that's the answers we're working on now, the questions we're working on now. So I'll touch very briefly on taste. So we can do, people have worked on, of course, the crazy Japanese people. This is Hiro Iwata, good friend of mine. So he developed a bite interface. So you can bite down on this device. And if you're biting into a cracker, it'll go, and if you're biting into like yogurt, it'll be squishy. Anyway, you have to try these to try it out. And so another example is Edible Bits. So this is a straw-like interface on the left. And you can choose different flavors, and the straw will produce a different flavor for you to eat. And this one I haven't tried on the right is the taste screen. So you actually lick the screen, and they display whatever's being shown on the screen. They display the proper taste that comes onto the screen, and then you lick the screen, and you can taste that particular food. I haven't tried that one. The other displays that people have come up with, these are lollipops that you can, sweets that you can suck on, and trying to get different tastes. I'll kind of leave you with this. I don't want to spoil anything, so I'll stop. There are other videos that I'm not going to show, but again, I don't know if they've been shown. But another one that you can look up on Vimeo is World Builder by Bruce Bennett, which really, again, has some really interesting, they explicitly show touch and smell, wind, and so on in the virtual environment. And they're mainly using brain stimulation to do that. And then another one is Sight. This is more of an AR one, and again, I would look these up if you're interested in seeing some interesting views about interacting in different ways. And these are kind of 2 VR, AR short films that are very interesting. So I'll leave on saying that, you know, Bowman et al. In their book came up with the kind of the big 5. So object selection, object manipulation, navigation, system control, symbolic input. And I added, I think avatar control is kind of another one that we need to talk about now that we didn't talk about back then. And all of these require a multisensory approach. And I feel really lucky to be working in a lab that really, you know, having worked on haptics for a long time, done some audio work, I studied computer graphics, and smell and taste are a little bit new. It's really nice to be at a place where we can focus on how these senses interplay with each other and how we can balance the strengths and weaknesses to produce a better environment. And and the last thing that we always do in virtual reality is throwing things. So a job simulator is a good example there. So anytime you can allow somebody to throw things in VR, you should, because in addition to object selection, manipulation, and navigation, throwing things seems to be really popular. My final thoughts is we could think about things like 3D printing objects and putting them in the scene. So let's say you had a robot arm that could place a cup right where the virtual cup is in real time. That could be pretty interesting from a passive haptics point of view. So there's some nice mashups we can do. If we think about real world stimuli is very, very high fidelity. So, you know, capturing images of the real world or textures of the real world, but we don't have a lot of control of how to change them. Computer-generated stimuli is much lower fidelity, typically lower fidelity, but we have complete control over what they look like and sound like and everything else. So the question is how to mix them. And also in thinking about this, if you think about the later we mix, the more personal the stimuli. So if you mix in the environment, other people can also see and hear what you're doing. If you mix in the cochlea, it's really only you that can understand or experience what's going on. So those become more personal or more discrete. And these multisensory approaches I think are interesting because they can compensate for the strengths and weaknesses. And yeah, so I will leave it there. And I will stop sharing. Hopefully I went in time.
Thanks a lot, Rob, for your talk.